So we will start the webinar right now. Thank you all for logging in and participating in this webinar. So the plan today, let's see if I can switch over to the this presentation, is to give first a short introduction to myself and to the company Verst Engineering. Then I will do a live demonstration of different features of the MCalibration software. And then we will end with some questions and answers at about 45 minutes from now. Two things before we get started. The first one is that this webinar is being recorded, so keep that in mind. The second one is that if you have any questions about any of the topics that I'm going through here today, please write your questions into the question window of the GoToWebinar web or the application that you should have on your screen. We will probably not answer them live right when you ask them, but I will try to get to them at the end of the webinar. So let me just do, as I said, a quick little introduction that we get into the core topic of our presentation today. And I should also mention that this webinar is the second webinar in our MCalibration series. This is advanced use of MCalibration. About a month ago, I gave a webinar that was an introduction to the MCalibration software. My name is Jörgen Bergström. I work at Verst Engineering, and I have a PhD in polymer modeling. And what I do every day, see if I can make this full screen, maybe it will look a little easier to read, is to solve problems related to polymer modeling, polymer experimentation, polymer failure, and advanced simulations in general. I wrote a book recently called Mechanics of Solid Polymers that I encourage you to take a look at if you're interested in any of these topics that we cover today. I also teach a number of other longer training classes that I will talk about towards the end of this webinar. Verst Engineering is a consulting company. We focus on a few different topics here at this company. We specialize in failure analysis, material science, and mechanical engineering. The work that I do is mainly related to polymers and polymer behavior. And we also have these softwares called MCalibration and PolyUmod, and that's the topic of our webinar here today. We here in the company do a lot of different work related to mechanical testing. I think mechanical testing is one of these topics that is more important than a lot of people realize. So we have developed our own test lab. It's a very advanced test lab that we can measure the mechanical properties of virtually any polymeric material and also some non-polymeric materials. We also have developed advanced software that gives you more accurate predictions that you can get using many of the built-in material models that come with finite element softwares. And we also have expertise in nonlinear and multi-physics simulations. And this is an area that becomes more and more interesting to a lot of people when you have multiple physics or principles happening at once. So you want to take that into account into your finite element simulation, and that requires specialized information and software and knowledge, and we help a lot of companies and people in that area as well. And when it comes to mechanical testing, we do a lot of testing here related to the generic mechanical properties. We do, as you can see on the images here, tension testing, compression testing. We do fracture and failure testing as well these days a lot. We have a very advanced set of tools for high rate and impact testing as well. Most of the experiments we do use digital image correlation to measure the strain field during the test. So we can look at the whole distribution of deformation that occurs to guide the analysis of the products that we're studying in the end. The software that I will talk about here today is the PolyUmod software and the MCalibration software. So PolyUmod is a library of advanced use of material models. So it's a plugin that sits inside or is used by the Finite Element software. It's a shared library file, so you can't really see what it's doing, but it's being called by the Finite Element software at each integration point, typically during a simulation, to calculate stress and strain for the analysis. So that's very useful because it provides more advanced material models than what's often available in the FE software itself. But to use those material models, you need to have material parameters that describe the specific properties of the type of polymer that you're studying. So that's where the MCalibration is useful, because it's an application, it's a traditional application that can calibrate any of these material models that you may be interested in. That is the polyUMOD material models, but also built-in material models in Abacus, ANSYS, LS-DYNA, MSC Mark, COMSOL, etc. So it takes the experimental data and gives you the parameters that are needed for the finite element simulation. So that's what I want to talk about here today. How do you actually do this? What's the effective way of doing this so that this becomes a quick and robust procedure? The software, polyUMOD and MCalibration, can be installed on both Windows and Linux PCs. By default, the location of the files for Windows PC are in this directory listed here. They are using a license file, and they can either be a floating network license for polyUMOD, but MCalibration is a traditional application, so that's a node-locked license configuration that's used for that. What I want to do is, I don't want to spend too much time on that introduction beyond that quick review of some of the things that we have been doing and how this works. Instead, what I want to do here is I want to go through some case studies. I want to show you how I would work on a few different basic problems, so you can get a feel for how you would use this software to quickly calibrate different material models. So what I have done is I have created a test case here that I'm going to start working on, and I will demonstrate different features of the software as I work on this test case. So I saved these files in this directory. There are 11 different experimental tests that were performed on a polyether-ether ketone peak thermoplastic material. And here they are. They're named as test 1, 2, 3 up to 11. When I get the experimental data, the first thing I typically do is I open it up and see what is this data, and it just has a name, right? So it's going to open one of these files. So right-click on it and I open it with a text editor. So here's the contents of this file. You see that it contains 3 columns of data. It's not quite clear what these are, perhaps. So luckily for us, though, there's a README file here. So if I open that file, it says that this was testing that was performed at room temperature, and the 3 columns are time, engineering strain, and engineering stress in megapascals. Okay, so that's pretty basic, pretty common situation. So I'm going to now take these experimental files and try to analyze them and come up with a material model that can be used to predict this behavior. So what I will do is I will arrange my windows a little bit here. I'm going to start the MCalibration software by just clicking on the icon at the bottom here, and it opens up the software. As I mentioned in the introductory webinar about this software, there are 5 different sections of the application here. There's welcome, tutorials, that has some introduction tutorial material. Data is the section that you can use, and I will demonstrate that here today, to manipulate experimental data, or I should say clean up and make it useful for calibration purposes. Calibrate is where we actually analyze the data and find the properties that go into the material models. And library is where you can have already calibrated material models. So here, what I will do is I just open this window here. There are different ways, as I mentioned in the previous webinar, of getting experimental data into this application. One way you can do is you can just select these 11 files and just drag and drop them over. If you do that, and then you have to wait a few seconds while it reads in these files. So it reads it in, and as you see here, I'm going to maximize the window. It read in the files here. So in this window now is the calibrate section of the application. There are 11 different load cases that are these 11 files. And then it plots to the right the data that was in these files. In this case, for me, it plotted true stress and true strain, even though the experimental data in the file that we just opened a second ago was engineering stress and engineering strain. So you can switch here between engineering stress and strain by clicking on the E button or the T with true stress and true strain. So you can go back and forth. In this case, there is no way you can actually completely convert an engineering stress strain data set to true stress and strain because we didn't know the transverse strain. We don't know the Poisson's ratio. So what the software does in a case like that is that it assumes that the volume is preserved during the deformation, and therefore you can then calculate the true stress or approximate true stress from the engineering stress. But I will stick to the engineering stress strain here because that was the actual data that was recorded in these experiments. We have, in this case, a lot of files and a lot of curves here. So there are a few things that are kind of useful to keep in mind when you have something like this, is that if you click on one of these tests here, the corresponding line in the graph is highlighted with a thicker line. You can kind of figure out what test 3 is, this one over here, because of that. Another way to select the load case is you can click on the curve in here and it selects the corresponding load case that that line corresponds to. You can also look at the definition of these different tests or these different experiments by just double-clicking on one of these, test 3, and I get the dialog box that talks about this particular experimental test. This one is an experimental data type. It's a time, stress, and strain type experiment. And the loading mode is selected to be uniaxial. And if it wasn't uniaxial, you would have to fix that, of course. And there's some other settings here that I will not talk about right now. You can also double-click on one of these curves. If you double-click on one of these curves, then it will also select the corresponding load case, and you can edit it that way. So you can work with the list here or with the graph, whatever is more convenient for you. The next thing I want to do here is that these tests have names that are not very descriptive of what's going on. So I'm going to select all of them. I click on the first, I shift click on the last to select all of them in here. Then I go to the menu load cases. And in this menu, there is a choice here, rename load cases based on type. So if I click on this one, it will rename these files and give them a little bit more descriptive information about what the different files were. So this says uniaxial compression, and then it has an average strain rate listed here. So I can kind of see what these tests were. So this is a little bit more useful to me than the previous on the names from the data file. So sometimes that's a useful thing to do. What I will do now is I will save this file. So I'm saving this information that I created here in MCalibration so I can come back to it if I want to. So if I close this file, I see that this is the file that I created. This is containing now all the experimental data from these different experiments. Before I start selecting and calibrating different material models, what I want to do is I want to make sure that these experimental files have been organized and are suitable for material model calibration. And often, if you get experimental data from a test lab, it could be your test lab or some other test lab, the data you receive is actually not directly suitable for calibration. You may want to do something about it to make it more suitable. So I'm going to give an example of that issue here. So I'm going to click on the first one. And I want to look at the data that is in this experimental test. So if I select this one, I go to load case and edit the experimental data for this load case. What happens when I selected that is that the information in here was loaded, copied over to the data tab. So now we have all the experimental data that was read in from that external text file or CSV file into here. And this is a region of the software where I can manipulate the data or clean it up or make it more suitable for calibration. The table shows the data. There are a number of operations you can apply to this data here. And you can plot the data to the right. It's just select which column you want to plot. It doesn't really do anything except represent graphically the data itself. But there are a few things that I see here that is concerning to me, and this is the purpose of this demonstration, that we see that here's the time column, and the time column is increasing, and the start time here is not 0. It starts with a time of 0.44. So when you run, think of it this way, when you run a finite element simulation using Abacus, ANSYS, or some other software, at the start of that finite element simulation, what is the time? The time is 0, right? And then time will increase in a finite element simulation. Similarly, when you run an experiment, at the time when you start your experiment, the time should be 0 and then increase. So what I will do here is I will make these data points in this time column start from 0. Because it really, at the start of the test, the strain should be 0, the stress should be 0, and the time should be 0. So I'm selecting this column, and I say make column start from 0. So what it's doing, if you select this, it subtracts the initial value from all of the other values in this column. And by doing that, I have modified this file, and it starts from 0. So this is really what I wanted to do. It looks like it's in proper format now. The strain is already starting from 0, but the stress has a finite value, and this is pretty common too, that people preload their specimen a little bit perhaps, and then they start recording the test. But that's kind of a cumbersome too. Think of it again from a finite element viewpoint. If you create a finite element simulation, typically you don't start at time 0 with a finite stress in your system. You typically start with it unloaded, and then you generate loads and stresses in it. When we calibrate the material model, we don't want to have a finite stress at 0 strain, typically. So I'm going to make these stresses start from 0 as well. There are two ways to do it that are pretty easy. One is to just write 0 here. I can replace this value with 0. So that's one way. The other way is to take this value and subtract it from the rest of the numbers in this column. So you shift the whole curve up and down. And which of these approaches is best will depend on the situation. Here, I'm just going to shift it all with the initial value. So that's good. The next thing I want to do here, and this is also very common when you have experimental data, is that if you look in this header here, it says that this data file has 8,500 data points. So clearly this experiment was run with a lot of different, high data acquisition rate, more so than you need for calibration. So if I plot strain versus stress here, you see this is 8,000 data points along this curve. When we calibrate the material model, what the software will do by default, and you can change this, is to follow the strain exactly, point by point. So it takes 8,500 increments to reproduce this experiment. And you don't typically run a finite element simulation with 8,500 increment, at least not an implicit simulation. So here, it makes sense to scale down or reduce the number of data points because we don't need that to be so many. It just makes the calibration slower and it makes the data files larger. So I'm going to change the number of data points. So I'm clicking on that button. I'm just going to make it say 500. If I click OK here, the curve will not look much different except that it has less data points, and therefore it would be more suitable for calibration purposes. So I'm saving this to the load case by clicking on this button. It takes the data that we have here now and loads it back into this load case. So here, if I double click on the first one, now it contains 500 data points, and initially it was 8,500. So that's good. Now that is good to go. If I take one of these other guys, I click on edit the experimental data to see what's in here. We'll see this one has 1,000 data points. Okay, then maybe that's good enough. What I could do is I can say, well, I want to make sure that all of these files, all of these experimental files, don't have too many data points. Instead of doing it one by one, as we just did, I can use another feature here, clean up the experimental data using this icon. So I'm clicking on this. I get a dialog box that asks me what I want to do. Here I want to make sure that no data file has more than 500 data points. Okay, that maybe is good enough. And you can also upsample if you have too few, but I don't want to do that. And I don't want to truncate the data. So I'm going to keep it this way. I'm going to say, okay. Now it will go through all of these files and downsample them if needed. So there are not too many data points in the file. Here we go. So I can save this file and we have it all saved in case we want to start over at some point. So far so good. The next thing I want to mention here is units. So MCalibration, you can see there says engineering stress MPa, megapascals. So how does it know this is megapascals? What if you want something else? How does units work here? You may remember that some finite element software like Abacus does not have units. It never will ask you what the units are. Other software like ANSYS specifically asks you what units you have. So people have different opinions about units. If you should specify it or not, if it should be self-consistent, or if you need to be explicitly specifying what they are. Here, in this software, in MCalibration, you can specify the units here under the preferences units. So this is the default set of units that I have selected here, millimeters, Newton, seconds, and Kelvin. From this, then the stress will be in units of megapascal. If you don't want to do it, you can specify other base units in inches, for example, and pounds, if that's what your preferred set of units is. But really, units are not used particularly in the software. It's just for the graph. It likes to have the MPa here or PSI or whatever you have. Units are also used in one other location in the software. If you want to export the material model, before I export it, I need to select the material model. So I'm just going to quickly select the material model. I'm going to select the PolyUmod 3 network model. I have now a material model here. Say this is the material model that I want to use. I want to export it to Abacus or ANSYS or LS-DYNA or some other FE software. I export it, and there is units here. You can select what units the parameters are exported in. So you can internally work in millimeters and then export it to inches or whatever situation you have. So that's how units work. You don't necessarily need to worry about it, but if you want to take that into account and you want to convert units, you can do it, just like I showed. Okay, so I selected a material model here, the 3 network model from the PolyUmod library. It's a pretty basic material model in my mind. It's a viscoplastic material model that is very well suited for thermoplastics. It's my go-to material model for thermoplastics. If I can use it, I will use it, if it's accurate enough. So I selected it here. When you select the material model like I just did, it populates this table here with the parameters that describe this model. So this is the shear modulus that the software thinks is a good guess, but it hasn't actually searched for it yet. So if I click run once, the software will run through all of these different load cases. That is, it will follow them, basically create a finite element model, run it internally, and then plot the results using the parameters that are given down here. And it took 1.1 seconds to run all 11 of these. Now the graph looks absolutely difficult to read, so I'm going to hide the legend. We can see it a little better because there's so many tests that were part of this. We'll see that the calibration is not particularly good. The dashed lines are the predictions, the solid lines are the experimental data. But we haven't really searched for these parameters yet. I'm going to save this, and before we search for material parameters, there are a few other things that I think are worth mentioning here. That is, in this case, I have this model here. I have some load cases or experimental files. There's sometimes you want to copy information from one calibration to another, and there are different ways to do that in a very quick way. So I'm going to show that. So if I file new calibration window, and I put them side by side here, if you can see it. In the second window on the right here, there is nothing. I don't have any experimental data. I don't have any material model. Say I want to take the last 3 experimental files here and put them over here. What I can do is I select them, and I have to make this window a little bigger. I select them, and I click on this copy. So copy load cases to the clipboard. So it copies these load cases to the clipboard. Then I go over here, and I can just paste the load cases. So you can copy load cases from one window to another, like this. Similarly, you can copy a material model. If this is a really good material model, you may want to keep it somewhere. So you copy that, and you go over to another one, and you can paste it in, and paste it in right here. Then you can run this one, and it will show you the predictions just for that. So if you want to quickly copy models or experimental data, that's easy to do. It's also kind of interesting, perhaps, that if I select and copy this material model, I can, under results here, there is 4 tabs. This is runtime information. Comments is if you want to remember what's going on, like, okay, this is calibrating a model for peak, something like that. You can also put text here that gives information. So I copied the material model. I can paste the material model in here. So you can see the format of the information is this. So when you select either a material model or a load case, it converts it to this XML format, which is a text-based format. So you can see what's going on in it here. So that's sometimes useful if you want to copy it in here or to a text editor. So that's something you can do when you copy and paste material models. I'm going to close this window and go back to this main window that we started earlier. Okay, so here's our material model. Another feature that some people get a little confused about is this 1 versus 2 here. So the graph window can either be just showing one graph that it looks like, but if you click on 2, the 2 icon, then you can have 2 parallel graphs. You can plot 2 different things at once. And you can switch which of the 2 graphs is active by clicking on it. So this now, the right one is active. So on the right one, instead of plotting, I have true stress, true strain on the right, and I have engineering stress strain on the left. If I want to plot time on the x-axis on the one here, I can simply double click on the x-axis and click time, and I say okay. And then it plots time versus stress in this case on the right, and I plot engineering stress strain on the left. You know, if you like to see 2 different things at once, that can be useful. I'm just going to switch back to the main graph here for now. Okay, now let's see if we can calibrate this material model a little bit. Before I calibrate the material model, there are 2 things you want to do typically. The first one is you want to look at the parameters that were fed to you by the software. Or do you agree that this is the set of parameters that you want to work with? That is, some of them are red and they're selected to be optimized. So that means that this shear modulus is going to be searched for by the software. The next parameter is called theta hat. It's not selected to be optimized. It's always going to be 0 if you search for the parameters. And how do you search for parameters? You click on Run Calibration. But in this case, though, if you want to figure out why it's doing that, it's because theta hat happened to be a parameter that controls the temperature dependence of the model. So this parameter, if you make it non-zero, will give you a stress strain prediction that it's depending on the temperature of the actual data. In this case, all of these 11 files were performed at room temperature. So there is no point in figuring out how much the shear modulus changes with temperature, since all the data we have is at 1 temperature. So that's why this one is not selected to be searched for. But you can change what's searched for if you like. If you say, I really want A to be 0, A is determining, in this case, how different is the yield stress in compression versus tension. You could make it that way. So that's something to think about before you calibrate. Do you agree with the number of parameters that are being searched for here? The next thing that I typically do before I start calibrating is I go to preferences. Under the preference dialog box, there are two things that I like to look at. The first one is the global options. That tells me how many CPUs will be used to perform the calibration here. In this case, my PC has 8 CPUs and it will use all 8 of them, so that's fine. Typically, there is no reason why you wouldn't use as many cores or CPUs as you have available. The second one is the optimization method. So under optimization, there are two things that you can specify. The first one is what algorithm will the software use to calibrate the material model. And there is a selection of different optimization algorithms here. The one that I typically use is automatic extensive. So this is a method that automatically switches between different optimization methods to find the optimal set of parameters to match the data as well as possible. This method is robust and it usually does a good job, but it can be a little bit slow because it's very greedy and it doesn't give up very easily. And that can be good, right? But it means that the calibration is can take a little bit, can take an hour. For some complicated calibrations, I've been running calibrations for many hours, like overnight even, just to let the software try a lot of things. And that's okay. But the one thing that I want to highlight, is sort of a little hint, is that there is another reason why you want to think about what method is used, because there are some features of different optimization algorithms that can have consequences to what's going on. What I mean is, in this case, we'll see that the initial calibration is not that great. This curve is way too high compared to the experimental data. Excuse me. So, but I know that this set of parameters that were given by the software roughly have the right sort of ratios to them. So that it's been set up to be a good calibration if this would matching it. What you want to think about here in preferences is that if you use a certain optimization method, like the extensive one, the software will initially use an optimization method that allows for very large jumps in these parameters if it finds a set that's better. And that can mess up the ratios of these parameters, the sort of the structure of the model a little bit. So if your initial guess is not very good, but you know that the parameters should move just a little bit in certain directions to match the data better, I often switch to a different optimization method, the Nelder-Mead, the simplex method. The simplex method always takes very small steps in the gradient direction, and therefore will not make your parameters jump too much. It will make small changes slowly, and it will take a longer time to run, but it will give you, in the end, parameters that are relatively similar to these in the ratios and how they're arranged. So that can be a little bit useful if you have a set of parameters that are far from the real solution. But in this case, I don't need to worry about it because it's actually, most of the data here is in reasonably good shape. So I'm going to stop this one. And I'm going to go to preferences and switch over to the automatic, a quick one of the automatic, because that will typically run faster to find the optimal set of parameters for me. And you can follow the error here in this graph. It shows you the average error in percent now of this model to predict this whole data set. And it's going to get better and better the longer we wait. I want to, instead of sitting here looking at this, which may be exciting and all, but let's show something else. And this is the calibrated model tab over here. What's kind of interesting is sometimes you have a file like this MCalibration file contains all of this experimental data, and it contains this material model on the left. But it can also contain other material moles. So here in this calibrated mol, it shows that there is one mol that we have worked with, and that's the PolyUmod TN mol, 3-network mol. The best fitness we've found so far is 28.56, and this is the value we have right now. So this is this mol. If I switch to another mol, let's switch to Bergstrom-Boyce, which is a mol I developed for rubbers some time ago. It's not as good for thermoplastics, but maybe we can take a look at it. So I selected a different mol. We haven't lost the 3-network mol that we calibrated. It's already saved here in under calibrated mols. So if I click run once, we'll see that this is the prediction from this particular BB mol, the Bergstrom-Boyce mol. The best fitness we have found so far is 49. This is what we see here. We have the 3-network mol still saved here. So if I save this here, I can go back to the 3-network mol by selecting it here, and I say, click on the copy of the modifier, and move it over basically to this region. Now it's here, and it's also here. If I run once now, we jump back to the 3-network mol we had before. I can take this and just copy it over and run it at once. So I'm just clicking that. It copied that file over, and it ran it, and we're back to this one. So we can keep track of multiple mols that we work with here if we like. This BB mol has a description, calibrated with MCalibration. If I double click on this one, I can edit that, say test 1. This is my first calibration attempt with this one. What I can do now, say I really like this initial, like hypothetically, say you like this particular calibration with the BB mol, but you want to explore a different BB mol. We have different sets of parameters. You need in this table multiple lines that have the BB mol in it. So to achieve that, you need to lock it. So if you lock this one, this mol will stay in here. And if you run it once again, you will have a second line with the BB mol that happen to have the same value of the fitness, but they have different descriptions if we want that. I can calibrate the second one now. And at the same time, I kept the first one. Now the fitness is getting a little better. It's 41. I can look at how it converges to a more appropriate calibration. I'm just going to stop it. Of course, you know, we have a lot to talk about and we have limited time here. Now we see we have in our library here calibrated mols with the 3-network mol. We have the BB mol that we locked. And then we have the current BB mol that has an error of 40, which is a little bit better. But we see that the 3-network mol is more accurate so far, but we haven't really calibrated any of these in any careful way yet. But that's kind of how that works. Another thing that is not obvious but can be very useful when you calibrate material mols is to add experimental data that you may not think about. So I'm going to demonstrate this very quickly. In this case, I want to make sure that the material mol that I calibrate in the end has the Young's modulus that I like. So I'm going to select all of these. I'm going to go to load cases. I'm going to remove clear predicted data. So now it's only the experimental data that's shown here. At 1% strain, for this case, the modulus, 1% strain, the stress is 44. So that means that the Young's modulus is 4,400. So what I can do here, I can click on rezoom. So I just rescale the graph. I'm going to add a constraint here that I want my Young's modulus to be 4,400. So I go to add load case, add load case. I'm going to, instead of experimental data, I'm going to say Young's modulus. I'm going to say, I want the Young's modulus to be 4,400. And I'm going to only consider tension, in this case, up to 0.1% strain. I click OK. Then I have one more line here. If I run this once, you will see that there is an error associated with this load case. There's 48%. So right now, my material mol is not predicting this very well. But if I ran calibration with now, it will try to match all of these tests plus the constraint that the Young's modulus should be close to 4,400. If I select this and click on the information, we'll see that currently the Young's modulus of the mol is 2,000. So it's about half. So sometimes it's good to add these constraints if you really like to see a certain Young's modulus, for example. The last thing that we may have time for here is to talk about failure prediction. So I want to see if I can calibrate the failure model to this data. I'm going to deactivate some of the compression data. So I selected them by clicking on off. They're still defined, but they're not active. So I turn them off. I see the predictions only for the tension here. I want to use a failure model here. So if I go to set material model, you can see that I have the Bergstrom-Boyce here. Let's go back to the 3-network model. So I have the 3-network model here, calibrated. I'm going to run it once. Here it is. Now I have my 3-network model. I save it. I go to material model. Here's the 3-network model, the description of the theory. It has some additional features up here, particularly polyUMOD variable. It has a failure criterion type. And this material model can have 14 different types of failure models that are predefined for it. And I want to show you how you can work with some of these. But it's not clear how you would do it here. How would you actually use these things? So how to do that is you will need to actually take a look in the manual for this material model. So the 3-network model, it's described in the polyUMOD manual. So if I click on this icon here, I'll get a PDF file pop up. And in this file, there is a description about the 3-network model, but particularly what I'm interested in is failure model. And it's a little bit beyond what we have time to talk about here, but all of the polyUMOD material models take 16 initial parameters that are global control parameters. And it turns out that parameter 15 of these 16 describes if a failure should be considered or not. The failure type is described by parameter 15. And here are these 12 or 13 failure conditions that you have available to you. The one I want to demonstrate is number 12, for example. This is a very powerful one. It's kind of interesting because it's a failure model that is rate dependent and it's stress based. And it's developed by Christensen, and that's a reference here if you're interested in it. I will talk about all of these things in more detail in my other classes, my longer classes, but I just want to demonstrate how you would possibly calibrate this thing because it may seem impossible because it takes 6 parameters, and these 6 material parameters describe the failure of this material, and they should be given after the other material parameters. And that's the tricky part because when I selected this 3-network model, they are hidden. You don't see these extra 6 parameters that describe the failure. So to use this and to calibrate this, you would need to use a template. So for each of these types of material models, there are templates, material model templates. So clicking on polyUMOD template. If you click on, say, the 3-network model here, it fills in the template here. This is text I can modify myself. This is the definition of the parameters that are used. So if you look here, material parameter number 7 should be mu A. That's, I'm sorry, MA. So that's this line here. And we should define 6 additional parameters here to describe failure. So I can quickly do that, and I have it sort of prepared myself a little bit by saving a template. So here are the additional lines that I need to describe. So at the end of the 3-network model, I will just paste in these 6 additional parameters that correspond to these parameters here, T, T over C, etc. So this is the failure stress in tension. This is failure stress intervention divided by the failure stress in compression. These are strain rate effects. I also need to activate the failure by setting this to be failure type 12. If I save this now, I have a different material model that is a template-based material model. And here is failure type 12 is specified here. And the last 6 parameters now show up here. This is where I can work with this in a very direct way. If I click run once, it shows me the predictions here, and it resets some of the parameters from before. That's why it's a little lower. We would have to recalibrate it if we wanted to use it. But the point I want to show as part of our webinar today is I have these now available to me. I can modify these and search for them, try to match data by searching for them. So 100 megapascal failure in tension, we don't reach that. So if I make it a little lower, say 10, we get a very early failure. Maybe do a little larger. We'll see if we get different failures here. Depending what value I pick, we get the material model that fails at a certain point in time. And this is just one parameter. And you can modify these parameters to match your data if you have good experimental data for it. But we have run out of time. There's so much to talk about here, but I hope I gave you a little bit of hints for how I work on some of these problems. What I want to do now is I will wrap up and move back to our presentation, and we will wrap up the webinar and we take some questions. As I mentioned a little earlier today, I'm teaching a lot of other training classes. This is a webinar that's a free webinar that's focusing on the software MCalibration. In May, beginning of May, I'm teaching a class on finite element modeling of solid polymers, and there are some advanced classes, high strain rate testing, etc. Check out the Verist website at the bottom if you want to learn more about our training classes. There are longer and a little bit more in depth, so you can learn much more than what we talked about here. The other thing I want to point out is everyone who's listening in on this webinar today have been given a chance to try out this software. So you should have been given a try license. You should try it out, see what you think about it. If you have any problems, if you have any features you think we should add to it or any other feedback to us, you can use our online help center. So we have a really cool online help center where you can add questions, and it's a good way. It's kind of a ticket system, so we can keep track of what we say. We can have multiple people respond, so you typically get faster response that way. So keep that in mind and try it out if you have any questions or any feedback for us. So what I will do now is I will try to answer a few questions, see if we have any questions lined up here for us. We have just a few minutes for that before we end today. I see there is a lot of questions actually. If we don't get a chance to respond to all your questions, be patient. You can email it to us, but I think we will also try to answer your questions privately, because we want to make sure that all your questions have been answered. So I have a few questions. I'm just going to go through them, and then we'll end our webinar for today. So one question came in, is related to the 3-network model that I demonstrated here earlier. And this is a pretty common question. So if you have a 3-network model like this, I say this is a great model for thermoplastic. It can handle the viscoplastic response, the nonlinearities, the recovery, and all of that much better than plasticity models can, which is really the value of this model. So the question that I got here is, so what experimental data should I really have if I want to calibrate this material model? What is the minimum number of experiments is really what people want to know. And the answer to that is kind of interesting, I think. So I'm going to highlight all of these again. In this case, there is actually all the data you need here, and then probably more than you need, to be honest. You see that I only have a uniaxial data, and the reason for that is you actually only need uniaxial data to calibrate the 3-network model, because the hyperelasticity that this model is based on is the 8-chain hyperelastic model, and that can be calibrated using only uniaxial data. And the viscoplasticity that's in this model too can be calibrated uniquely from uniaxial data only. So there is no need to do plane strain, biaxial, or any of these other complicated loading modes if you don't want to. It's okay to do it, but it's not absolutely necessary. So that's why only uniaxial data is typically what I recommend. You do need different rates. You need to have different strain rates to determine how your material behaves in different strain rates, so you can capture the viscous effect, viscoplasticity effects of the material. You also really should have both tension and compression tests performed. And the reason for that is that the yield stress in tension can often be quite different than from compression. And if you look at this here in this graph, in tension, I don't have the strain rates really shown here, but it clearly looks like this material yields in tension at the failure, at the stress that is lower than what the corresponding yield stress is in compression. And that's something you can capture in this model. There's a parameter to control that here. That's the A parameter. So that's the beauty, right? You got to have that information though to find out how this really works. So those are the type of experiments I recommend. If you also have different temperatures, if you want to predict the response at a range of temperatures, you would have to repeat some of those experiments at multiple temperatures. But you don't need to run every experiment at every temperature. You can fill in the blanks between different temperatures with less experiments. So it sort of helps a little bit like that. But we do a lot of experiments here. If you need help with experimental testing, just contact me and we can set up a discussion to help you figure out what experiments would be the best for you, for example. Maybe we have a chance for one more question. And please feel free to ask more questions, even though we're running out of time. We will take, we'll record these questions and respond to them as I said earlier. Let's see. There are some questions about how do we get this into ANSYS. I don't think I have time to do that. Well, the one thing I want to mention, if you're an ANSYS user and you want to get this particular tree network model into ANSYS Workbench, maybe I can do it. I don't know if I will have time, but I'll try to do it. We'll see if I can pull this off. So I will take this model and put it into ANSYS Workbench. What I will do first is I will go to C Program Files Versed Engineering. So that's where PolyUMod is and MCalibration is installed. And I'm going to go to test cases ANSYS, test case 1. I'm going to copy this over to a temporary directory and see if I can, I can open Workbench here. This will take a little longer than I wanted, but I'll try it. So while it's trying to start ANSYS, and on this little computer I'm running on, it takes notoriously long to start ANSYS Workbench or any FE solver for that matter. What I do need to do here though is say this is my favorite material model here. I want to put this into ANSYS. What I would do is I need to export it. I export this model. I click on whatever FE solver I'm interested in. There could be ANSYS here. And I got it in ANSYS format. I can also export it in Abacus if I like. So I'm going to export it into Abacus while I wait for ANSYS. Here's the ANSYS window for me, but let's go back to here. Let me open another window. Lots of windows. The more windows, the better, right? And I'm going to go to temp, this one, demo. The file I created was this one and this one, and copy these over here. So the ANSYS file I exported from MCalibration is the file I need to put into ANSYS Workbench. Here they are, TB data, type style commands. And the Abacus file I exported just for the heck of it is a Python, Abacus Python file that you can run in Abacus CIE as a script to read it in that way. But if I go to Workbench, I have to restore the archive that I just created. Let's see if this works. It may be a little slow, but it's not a big file. And then I go to model here. So I'll see if this takes too long, then we'll stop, but I will try it just a little longer here. So it's loading mechanical for me, if I'm lucky. Let me see. Okay, I think it's working on it. I'm looking at my other screen and it seems like it's thinking about it. I do need to do one thing while this is loading. I need to go back to this file here. This is the file I exported. I'm just going to select all and copy it, but pressing Control C. I'm going to go to mechanical. I go to geometry, solid, and under solid I have a command snippet. I basically just paste it in, and I'm good to go. That is all you need to do. Then you need to set up the rest of the answers, whatever you're interested in, of course. This is a demo case, so it's not particularly exciting, but the material parameters go in right here. And once you've done that, you're good to go. You can simulate this just like you would any of the built-in material models in ANSYS. Anyway, that is the end of our webinar. I thank you all for participating, and we will get back to you with answers to your questions. Thank you all for participating, and I hope to see you or meet you at the next webinar. Take care. Bye.